Okay. Thank you, Alessandro. So, good. So welcome to the recitation sessions for the classes of 3D hadron structure. So my name is Andrea. As Alessandro said, I am a researcher at the University of Turin, INFN. But let's get to know each other a little bit better before getting started. So are you all grad students or are there postdocs as well? Postdocs? Okay, very good. So, and there are also more. Okay, very good. Excellent. Okay. So please raise the hands experimentalists in here. 2, 3, 4, 5, and I guess all the other ones are theorists. Is that right? So raise your hands, please. Okay, very good. Okay, so this is a phenomenology session. So, I mean, it doesn't matter if you are a theorist or an experimentalist, there is going to be something interesting for both all of you. The idea of the recitation sessions is to get your hands dirty with doing things, okay? So I will tell you a couple of things related to, as a continuation to what Maria Elena already told you. And then the idea is to give you the tools to try to do something by yourself, okay? So the idea is, of course, to present you exercises which are, I mean, they do represent what we face in research. Okay, so I mean they are good representation of the problems that we have to take care of when we do real research, but they are not as difficult as the real work. Okay, because it has to be pedagogical. So the idea, so we're gonna do 3 recitation sessions. So the first one is related to matching small and large transverse momenta. The second one is related to understanding where the non-perturbative corrections from hadron structure or hadronization are relevant. And the third one is related to a simple implementation of the QCD evolution equations. Okay. So today we start from the matching. So Elena told you that somehow when you describe an observable, which is differential with respect to transverse momentum, you have to match what is small and large compared to a certain Hard scale. Why do you think that's the case? Suppose you are an experimentalist and you go to the experimental cavern and you count events of, I don't know, semi-inclusive DIS. So you count pions in the final states, or you count lepton pairs if you do Drellian. Why do you think you have to take care of matching small and large transverse momenta? Forget about QCD. Just think about what you see in the detector. Yes. No. Don't be shy. I mean, suppose you count, I don't know, you have 100 pions in the detector. So why would you need to look both at the small transverse momentum and the large transverse momentum regime? Yes. Exactly. So you will have, I don't know, maybe 80 pions that happen to have low transverse momentum with respect to the Hard scale of the process. But you will, of course, have events where these pions have a very large transverse momentum. Okay, so your observable is something like that. So if you measure a cross section, okay. So if we consider, for example, a lepton scattering of a proton, then you have another lepton in the final state, you detect a pion, okay, and something else. Your cross-section is something similar. So this is the sigma in the QT. In here you have QT. QT is the transverse momentum of the intermediate photon, okay, in here. And say that, for example, your Q is the invariant mass of the exchange photon. So whenever you measure an observable, you will have events at large transverse momentum and events at low transverse momentum. So this is just life. I mean, that's what happens. From the theory point of view, then we have to understand how to describe this cross-section. And what happens is that, I mean, QCD tells us that At low transverse momentum, so if you are in here, okay, when Qt is smaller than the hard scale of the process, you have a certain theory, a certain factorization theorem. At large transverse momentum, there is something else. And I want to convince you that this makes sense. So if you are in here, in this regime, where the transverse momentum is small compared to the hard scale of the process, the theory framework that we use is TMD factorization, where the transverse momenta, the observed transverse momentum, Qt, is actually made out of the vector sum of the transverse momentum of the quarks involved in the process. So you have KTA and KTB. You have these two transverse momenta that sum to the observed transverse momentum. So if Qt is small, what does it mean for the two transverse momenta that you have in the TMD PDFs? Yes. Exactly. So let's say they are both small. Okay, so they are soft transverse momenta. So they will be inside, let's say, the part of the cross section that describe hadron structure. Okay, these are soft variables. Whereas if you are in this separate regime, the Qt that you measure is very hard. So it's not what you measure, the transverse momentum that you measure is related to a hard event, a hard emissions, a gluon that actually is emitted in the hard partonic interaction. Okay, so for that reason, you're not going to find that transverse momentum inside of the matrix elements that describe hadron structure. Okay, so in here, the transverse momentum is hard, related to the hard part of the cross section. In here, it's soft. So it's going to be informative about hadron structure or hadronization. Okay, so, but as we said, we have a smooth function. When you measure the cross section, you have a smooth function. So you have to find a way to describe these two regions. And actually here it's a matter of doing, it's a matter of choice up to some extent. So why is this important? As I was telling you, for example, you have to, when you measure a cross section, you have events all over the place, all over the Qt range, okay? And when the Qt is small, in Drelian, for example, you can describe the cross section using TMD factorization. And small here means that, for example, you can use TMD factorization, so this blue curve up to Q divided by 3, okay? So in this case, if I calculate the cross section until 30 GeV, because here you're producing a Z boson, so the hard scale is the mass of the Z boson. So up to 30 GeV, everything is fine. And in Drelian, this is pretty well defined. There's no ambiguity in this, okay? For semi-inclusive DIS, the story is different because the Qt that enters the factorization theorem is the Qt of the intermediate photon, but it's related to the PT of, so the transverse momentum of the observed hadron in the final state via Lorentz transformation that basically boils down to having a Qt equal to PHT divided by Z. So depending on the value of Z, and the value of Q, the events in the low transverse momentum region are going to be different. So for example, at small z, you see that, so the small transverse momentum region is the region at the left part of the blue vertical line. So at large z, you will have more events in the small transverse momentum region. At the small z, you have basically few events. Okay, so implementing these conditions in real life, it's difficult. Partly because of the kinematics, and partly because the matching prescriptions are complicated. So this is just to tell you that in real life, it's something fishy. Understanding what is small and what is large can be complicated. Okay, so suppose we have our cross section here, okay? And we want to understand from the theory point of view how to best describe the cross section at low transverse momentum, at large transverse momentum, and in the intermediate region. So in QCD, we define some approximators of the cross section. The first one is the so-called W term, which is a term that's calculated in TMD factorization. So this W basically is so if you're talking about Drelian, it's the convolution of two TMD PDFs. up to some extent. So you have F1, let me call it this way, F1 TMD cross F1 TMD. In semi-inclusive DIS, you would have F1 TMD cross D1 TMD, where this is a fragmentation function. So it's an approximator of the cross-section that's supposed to be, let's say, to work well when Qt is small compared to the hard scale, and when the hard scale is large compared to small m, where small m is a generic mass scale, for example, 1 GeV, okay, like the mass of the target. So if you are in this kinematic regime, the TMD term should work well. Then I want to understand how to describe this part here, okay, so the large Qt part. So this is supposed to be the W term, the approximator. Then I want to understand how to best describe this region here, and I do it by using fixed order perturbation theory. FO stands for fixed order, okay? So the fixed order term, which is calculated in collinear factorization, say, so the fixed order term should be F1 and F1 collinear for Trelian, or F1 and D1 collinear for semi-inclusive DIS, tells you how to calculate this part of the cross-section. Okay, so here you see that Q, the large scale, has to be larger than M, as before. But then you are in the region where Qt is large compared to the small scale of the process. So Qt doesn't need to be small, actually has to be large compared to, say, the mass of the target. Okay, and then there is another approximator that we need to use, which is the small Qt limit of the fixed order. So you take this one, okay, and you say, okay, I want to take the small Qt limit of this. You say, I don't know why, but trust me, I'm going to tell you like in a few minutes. Okay, so say W fixed order, and then in here we will need something which is called the asymptotic term. Okay, so once you define the approximator, there are several ways you can combine these approximators in order to smoothly describe your observable, your cross-section. So the first one is the so-called additive prescription. You take W for the small transverse momentum, then you have the fixed order for the large transverse momentum, and then you subtract the asymptotic part, Y. So by the way, what you have in parentheses here is also called the Y term, what Elena called the Y term. So this is the W plus Y prescription. So the asymptotic is defined as the small Qt limit of the fixed order. So what happens to this this term when Qt is small? No, another one. So once again, asymptotic term is defined as the small Qt limit of the fixed order. So if I look at this difference, when Qt approaches 0, what happens to this term in parentheses? What happens to the Y term in principle? What? Say it again. Almost. So the asymptotic is defined as the fixed order in the small Qt limit. So if I look at this difference in the small Qt limit, it's 0, okay? So this Y term cancels at low Qt. And this makes sense because W is defined to be the good approximator of the cross-section when Qt is small, okay? At large transverse momentum instead, what do you think it happens? So at large transverse momentum, everything should be described by the fixed order. So what would you expect? Which cancellation would you expect here? Exactly. So the asymptotic term should cancel the W. And then we will see if this is true, okay? So another way to combine these three ingredients is the so-called multiplicative prescription. Instead of taking the difference between fixed order and asymptotic, you take the ratio between, sorry, there is a typo here. I mean, forget about the plus. Should be a multiplication, okay. I will correct it after the session. So at small qt, fixed order and asymptotic, they approach the same value. So this ratio is equal to 1. Okay, so the cross-section is well approximated by W. And the same happens at large transverse momentum. So W and asymptotic, their ratio should go to 1. So the cross-section is actually described by the fixed order term. And then you can have other prescriptions where instead of calculating the asymptotic term, you just implement some sort of weighted average of the W and the fixed order. So you don't worry about what happens in here. You take an average of the W and the fixed order, which is weighted by a factor related to the errors associated to W and fixed order. So this is a little bit more numerical, okay? So they are, in principle, these prescriptions are all, they are equivalent, but in practice, they are not. Okay, and in practice, what happens is that depending on the kinematics, you have some of them work better and some others work in a worse way. So what I want you to play with at this point is a toy cross-section. Namely, let's assume that this is the truth. So when we measure, for example, the QT spectrum of Drellian or semi-inclusive DIS, you get something similar. Okay, so this is a functional form of the transverse momentum. And then you have two parameters, M and Q. So we're, once again, so you have M is some mass scale. Okay, say 1 GeV. And then Q is your hard scale. Okay, so I mean, assuming that this is what you know from your experiments, what I would suggest you to do is to open the only notebook that you find in the folder that Alessandro shared with you at the moment, and try to define the approximators, W, fixed order, and asymptotic. After you define the approximator, we can try to compute, to build together the W plus Y or the multiplicative prescription or the weighted average prescription. And we see in which way we can approximate this cross-section. Okay, so let's see. So let's everybody try to open the notebook, please. Because you don't have Colab installed in your drive, I think. You have to enable Colab and then you can open it. But I guess you tried yesterday to use you already used the Colab notebook yesterday, right? So okay. Okay. Great. So please, I would suggest that everybody makes a copy of this notebook in his or her own drive so that you can modify and save the notebook as much as you want. Okay. Let's see if I can make it a little bit larger. Okay. So I'm gonna walk among the desks and see if you need any help. So I think it's really interesting to use this toy example because it gives you a flavor of what's going on in the real world, but without all the complications that QCD brings in. So the assignment is to define the approximator W, fixed order, and asymptotic of the full cross-section, okay? you can implement one of the matching prescriptions that we discussed, for example, starting from the additive one, the W plus Y, and then you can play with the value of M and Q, which are defined in the very first cell, in the second one, sorry. So you have, for example, here you define the kinematics, right? So you have the value of M, which can be like 1 GeV, and then you can start from a value of the hard scale, which is pretty large, 10 GeV, okay? So here there is a model of the cross-section, which is exactly what you had on the slides. So maybe we can write it here as well for everyone's benefit. So your cross-section is it's Q square divided by UT square plus M square plus Q square times QT square plus M square. Okay, so this is the sigma. Okay, you see that in the code, I also introduced the definition of the W term, the TMD approximator, the fixed order, and the asymptotic, but I actually didn't write them. So because I think it's best if you do it, okay? So remember that the W is defined as the sigma, but with Q larger than M and Qt smaller than Q. Okay, so you have to apply these two limits to the sigma. The fixed order is actually the same thing with respect to M and Q, but you have Qt much larger than M. And the asymptotic is you take the fixed order and you calculate it as the Qt, the small Qt limit of the fixed order. Okay. So once you do that, once you code, I think you have some experience with Python, but if you don't, it's just a matter of copying the function here, the definition of this function here, and applying the limits that I told you on the. Okay. So did everybody succeed in opening the notebook? So what's the W term in this case? How would you define W? Yes. So okay, let's keep Q squared at the numerator. Then what we do. So M squared, we don't have M squared because it's larger than Q. So we should have only Q squared here, you say, in the first one. And then in the second one, we keep both. So exactly. It should be 1 over Qt squared plus M squared. Okay. Does everybody agree on this? Okay. All right. Exactly. So the W is 1 over Qt squared plus M squared. What about the fixed order instead? Okay, let's see. So in QCD, it's not that simple, but this is just the exercise. So let's see. Yeah. then, yeah, qt square plus q square. Because you drop m square, and then you keep, you also drop m square with respect to qt and q. And why I'm not dropping qt, why am I not dropping q square with respect to qt square? So we said, okay, qt is larger than m, so we can drop m. Why? So we drop m here, but why am I not dropping q with respect to qt? Exactly. So exactly. So in principle, they can be of the same order of magnitude. Okay. So the fixed order expression is actually this one, as we said. Qt, exactly. Then what about the asymptotic limit? What about the asymptotic limit? The asymptotic limit is defined as the low Qt limit of the fixed order. Yes? What do I get? 1 over Qt square. Okay. Because Qt is small compared to Q, so this is Q square cancel with this Q square, so I'm left with 1 over Qt square. Okay. So we have our three approximators, W, fixed order, and asymptotic. Okay. So let's try to build the additive matching. Okay. So please implement Y as the difference of fixed order and asymptotic. And you in the following cells, you should be able to, just a second. Okay. That's the Y, the definition of the Y function. Then you can define this additive matching as W plus Y. And then you can compare it to, you can forget for the moment about the multiplicative matching and the other one, which is the matching as a weighted average. I would suggest you to define the additive matching and then compare the sigma and W plus Y. Okay. So you should be able to make a plot of the full cross section and the additive matching procedure and see what happens. On the other side. I want to see it live. Let's see what happens. You have a fox running on the bar. Is it just you, or is it? Okay, okay, cool. So did anyone succeed yet in comparing the two? I think you have to uncomment or uncomment some of the lines, because so the first one, so this cell here plots the sigma and the free approximators, the matching ingredients. Okay, the second one plots the sigma and one or all of the matching prescriptions. So for example, if you want to plot the full cross section, use this line, and then here you have to select your favorite matching prescription. So you, for example, the additive one You just have to uncomment the first, for the W plus Y, you just have to use this line here. Okay. ah, so this is but you know, you have to define exactly. Okay, so I see a comparison here. Okay, so here you're comparing the sigma and the additive prescription. So you see that this is a plot of the two curves on a range of QT that goes from 0 to twice the value of the hard scale. Okay, so you have a vertical line for QT equal Q. Okay, so what would you say? So one of your colleagues already got the comparison between the two curves. What would you say? Does it work well? Okay, it works pretty well, right? So if for this value of m and q, so if you have m equal 1 GeV and q equal 10 GeV, you get a very good agreement between the sigma, the full cross section, and the additive matching prescription. Okay. So now I suggest you to plot the same thing, you do the same comparison, but lowering the value of the hard scale. Try to use first 5 GeV and then 3 GeV and see what happens. So you should be able to change the value of Q in one of the first cells. Okay, so say this is representative, 10 GeV is representative of, for example, semi-inclusive DIS at collider mode, for example, at HERA, whereas 3 GeV is the typical value of Q, even, I mean, a bit lower usually, maybe 2. It's the typical value of the hard scale for semi-inclusive DIS at fixed target energy, say COMPASS or Hermes or even JLab data. Okay. So try to see what happens to this matching prescription when you change the kinematics. Try to play with the value of Q. Once you plot the sigma and W plus Y on the same panel, try to see what happens if you change Q to exactly 2 GeV or exactly. These are the approximators, exactly. Okay. And did you already execute this cell again? Yeah, okay. So what would you say? Okay, let's see. So the exactly. Okay, so it should be good. Forget about these ones. Multiplicative matching and weighted average, forget about it for the moment. Okay, so what would you say? Okay. So the agreement gets worse when Q is small, okay? Okay. So this is a hint at what happens in real life. Okay, so these prescriptions here are based on these limits. Okay. So these prescriptions are based on these limits. So if these limits are, let's say, just approximate or not very well satisfied, of course, the matching prescription does not really reproduce your truth. On top of this, different matching prescriptions perform differently when the scale Q is low. Before lunchtime, so I think we still have 10 minutes, right? So I would suggest you to implement also the multiplicative matching and compare. So you should compare actually the sigma, W plus Y, and the multiplicative matching, and see what happens. So try to plot on the same panel, please, the sigma, W plus Y, and W times fixed order divided by the asymptotic term. So instead of having two curves, let's look at the three curves all together. And I mean, try to change also the value of Q. See what happens for 10 GV, 5 GV, or 3 GV. The multiplicative, there was a cell to define the multiplicative matching, which is actually in here. So here, okay, let me see. This is a cell to define the weighted average, but we don't have time to look at this. You can have a look at it later. If you don't fall asleep tonight, for example, you have a good homework. Multiplicative matching. You have to implement W times fixed order divided by the asymptotic. Let me do it as well here. Yes. Oop. What's the first case? Okay. Okay, so you compare the cross section and W plus Y. For which value of Q? What's the value, sorry? I don't know, I don't remember which one I put in there. No, but Q. What's the value of Q? The one which is hard code? 10. 10. Okay, so, and then what happens if you include the multiplicative prescription on top of the two curves that you showed me? That's a spoiler, yeah, that's okay, then it means it's not implemented correctly, probably. What's the value of Q here? 10. No, they should be actually the same. Okay. So when Q is large, you see that the full cross section, the W plus Y, and the multiplicative prescription, they perform equally well. Okay. And something different happens at lower energies. Let's see what happens. So if I change my hard scale to Q equal 3, for example, okay, what do you observe? So d sigma is your truth, okay? And then what happens to the two matching prescriptions? At large transverse momentum, okay, it's as good as before. Okay. Mm? Okay, so if we look at the large transverse momentum region, I mean, both prescriptions are equally okay. Okay. At low transverse momentum, instead, the additive prescription works better than the multiplicative one. Okay, so you might wonder, okay, so who expected this? Did anyone expect this to happen? Nobody expected this to happen? Alessandro, no. Okay. Exactly. I mean, so one of the nice things of playing with a model is that you can actually do the math exactly and see what's happening. Okay. So so who actually, before I tell you, let me ask you. So how would you explain this feature, this behavior, by looking at these limits here? What would you say it's happening? You you don't need to do the math. Just think about what's happening here. So when you take these limits, effectively what you're doing to the cross section is to, reorganize this expression using powers of m divided by q and qt divided by q. Okay, so you have some terms which are proportional to m over q or qt divided by q to power 0, and then you have power corrections which are proportional to powers of m over q and qt over q. These go under the name of power corrections. So when you take the multiplicative matching, some of these power corrections are less cancelled compared to the, they cancel in a different way compared to the W plus Y prescription. So it's basically like having some coefficients, some powers that are, they need to cancel with each other, but if Q is small, this cancellation does not work equally well in the two prescriptions. If Q is large, no problem. But if Q is small, you have to be careful about what you do here. Okay. So, for example, the multiplicative prescription, the green one, is widely used in high energy physics. When you talk about, for example, the Higgs PT spectrum or other high energy processes, whereas you never find it in the literature of semi-inclusive DES at fixed target energies, because, this is one of the reasons, actually. So the matching in general at the level of semi-inclusive DIS at low energies is not very well understood yet. So this is a very active line of research. People are actually working on it. We have hands-on on this problem. When people do phenomenology of TMDs, like Elena showed you, we don't take into account the matching, even if we have plenty of data in the matching region. And that's because we don't know exactly what to do in order to build a reliable matching prescription. So this toy model is just to tell you what the potential problems could be, but in QCD is of course a little bit more complicated. So if you're interested to know more about this, we can certainly talk about it today, tomorrow, whenever you want. But for now, I think it's time to pause and go to lunch. Okay, so the notebooks are online. I will upload more material related to the exercises that we will do on Friday. But of course, feel free to ask if you have questions.